Hello and welcome. Today is our first day where we're talking about topics from chapter 15. So as a big overview, chapter 14 was mostly about differentiation. We talked about partial derivatives, we talked about taking gradients, and those are both things that have to do with derivatives. Now we're going to move into integration. So integration for multivariable functions. Today, our learning goals are to geometrically describe the process of Riemann integration for several variables, meaning multivariable functions. We're also going to compute double integrals over rectangular regions. In the next section, 15.4, we'll talk about computing them over more general regions other than rectangles, but we'll start with rectangles. And as we compute these double integrals, we're going to highlight two different techniques. One is the separation of variable technique, and another technique is to interchange the order of integration variable technique. Finally, we should be able to state and apply Fubini's theorem. Fubini's theorem is exactly the fact that we can interchange our order of integration. That's it, I think. So to get started with Riemann integration for multivariable functions, let's do a quick recap of what we know about Riemann integration from single variable functions. So let's say that I have a function here. Here's my x-axis, here's my y-axis, here's my function f of x, and I want to be able to integrate from this point x equals a to x equals b. The way that we started out talking about this back in the day is that we would break this interval ab up into rectangular pieces, right? And this integral was the area under the curve between the values x equals a and x equals b. And when we initially estimated what this area is, we would pick some point in the interval. Sometimes it was the left endpoint, sometimes it was the right endpoint, sometimes it was the midpoint, and all of these are going to give us different estimates for what the area of this curve is. So if I were to pick left endpoints, I would end up with a series of rectangles that look something like this. And so I'll write what that sum looks like here in black, I guess. So here I'm summing over n regions. So my I is going to go from 1 to n of, well, what is each of these regions? Each of these regions are triangles where the height of the triangle is going to be given by whatever the left endpoint is. And so I'm going to plug in f of x sub I, meaning that these x sub i's increment up as I change my I value. And I'm summing them times the width of each of the rectangles. The width of each of the rectangles is typically written delta x, meaning that delta x is the width of this rectangle, and f of x sub I is telling me what is my output at this functional value, where this one probably is x sub 2, because it's the second rectangle. And it's the height of the rectangle, height, times the width. And this is an estimation of the area under the curve from A to B, but obviously we don't want just an estimation, we want to make this more exact. So Riemann integration tells us that we're going to take the limit as n goes to infinity, meaning that we're going to make more and more and more of these rectangles. And as we get more and more of these rectangles, our little width of the rectangle is going to get smaller and smaller and smaller. And this sum is going to be equal to exactly what we want it to be equal to. It's going to be the integral from a to b of f of x dx. So the width of the rectangle is taken care of with this differential, and the height evaluated at each of those x values is given by this term f of x. So this is just a recap of what Riemann integration looks like for single variable functions. Let's compare that to what we find for multivariable functions. So let's say now I have an example of a multivariable function. So my inputs are from the xy plane, and my outputs are up here, my z values, and the graph of this is this curvy sheet, which is my f of xy. And instead of integrating just from a to b, like we did with a single variable function, now we're going to integrate over some rectangular region. So my region in this case, the notation for regions, it's going to be the interval AB crossed with the interval CD, where it's convention that we always do the x-coordinate first and the y-coordinate second. And so this rectangular region is something that looks like a box, where I start, my x values are going from A to B, and my y values are going from C to D. There. So that's my region of integration. And really, what I'm trying to compute is, what is the volume of the region? I'll get another color. What is the volume of the region if I were to cut out this box, where the corners of this box are up here on this wavy sheet? So essentially, this is a box with some sort of square bottom, but a wiggly top. And the height, the whole volume of this object, maybe I should draw these in solid so it gives us a better idea of what the volume looks like. With a base down here in the xy plane, and the height is this wiggly top that we find that's given by the f of xy function. And I want to know, if I were to find the volume of whatever this big box region is, that's exactly what my integration is telling me. So how do we go about integrating that? It's exactly the same technique that we saw before, only this time we're going to do it for 2 dimensions in the base rather than just a single dimension. So just like before, I'm going to break up my rectangular region into lots of little intervals. Only this time, because I'm breaking them in both the x and the y direction, I'm going to end up with a bunch of little squares down here in the base. And for each little square, I can pick a point in this square, and the height of that is going to give me some rectangular box. So if I pick this square, I'm going to pick a point in that square. It could be the left endpoint, it could be the right endpoint, but notice that there are lots of end points because it's a rectangle instead of a square, or instead of an interval. So I pick a point in this region, and I find the volume. Whoops, this didn't connect to the right place. The volume of this rectangular region is going to be the volume that we sum over. So what is the volume of this region? The volume of this region is going to be the area of the base, and in this case, the area of the base is given by delta x, delta y, meaning that it's the width in the x direction, given by delta x, and it's the width of the base in the y direction, delta y. So this is the area of the base. And what is the height in this case? Well, I just pick some point that's in this rectangular region, and I see how high is that point. So I'll call that point x sub I, y sub j. And I want to know what is the height of that point. I plug it into my function f, and that gives me my output f of x sub I, y sub j. So this is my height. So I have area of the base times the height, and then I need to sum up all of them, because this is just for one rectangular region, and I want every single one of these rectangular regions. So to get every single one of these rectangular regions, I have to sum across all of the x1s. So my I is going to go from 1 to n. But I also have to sum across all the ones that go in the y direction as well. So I end up with a double sum. Maybe you haven't seen double sum notation before. Really, it's exactly what you think it should be, that I'm going to sum up all of the boxes that go this way and all of the boxes that go this way. And if I take this whole big sum, that'll give me an approximate volume of this region under this curve with this rectangular base. But this is just an approximation, that we didn't exactly compute exactly the height in each of the places, because there's going to be a little variation as this curvy thing curves. So that's where calculus comes in. And calculus says, this is what Riemann integration is. When I take this limit, as both m and n go to infinity, meaning I'm getting more and more and more of these little boxes, then the area of these bases are going to shrink because the change in x and the change in y's are going to get smaller and smaller as I get more of these boxes. And as I take this limit, this is where we get our definition of Riemann integration. This ends up being the integral as y goes from c to d, the integral as x goes from a to b of f of xy dx dy. If this limit exists, then this is how we define our Riemann integration. So maybe this is something that I should box, because this is our definition of double integral. Definition of double integral. So if this limit exists, then this is what our double integral is. There are a couple of things that I want to point out. So unlike single integration, this interior part is exactly what we saw before with normal integration. Only now we're also integrating it in the y direction as well. The thing that I want to note now, and I will continue to note throughout the lesson, is the fact that I will frequently label the variable that we're talking about for these integrations. Unlike before, we knew that we were always integrating with respect to x. Here, the interior integral is with respect to x. It always must match the interior differential, meaning that my interior is dx, then my interior integral is my x coordinates. And similarly, my exterior is a y, so my exterior differential is a dy. And we'll see why that's important when we start interchanging the orders of integration. So let's look at our first example of double integration. Let's say I have a rectangular region where my x-coordinates are going from 0 to 3, and my y-coordinates are going from 0 to 2. And my function in this case is the function f of xy equals 3xy. So when I set this up to integrate, I'm going to put my y's on the outside. My y's are going from 0 to 2. My x values in this case are going from 0 to 3. My function is 3xy. And this is in terms of dx dy. So how do I actually compute this integral? Algebraically, it's similar to the concept that we had with partial differentiation. I'm going to start at the inside and work my way outwards. So starting at the inside, I could think of putting parentheses here. You don't need to do that. But I'm thinking to myself, this inner integral is what I'm going to compute first, and the inner integral is an integral with respect to x. In this case, I'm treating y as a constant. So when I take the integral with respect to x, my y is a constant, just like when we did partial differentiation. So that means that when I integrate this inner portion, I'm leaving the outer portion alone. I'll just rewrite the outer portion, that y is still going from 0 to 2 dy. Integrating this inner portion, treating y as a constant, I think about treating x as my variable. What's the integral of x? The integral of x is going to be x squared times 1/2. And the 3 and the y are just constants that I can bring along for the road. So I integrated this inner integral, but I also have to evaluate it along the bounds. Maybe I'll keep parentheses here to keep track of my work. So I'm evaluating it from x equals 0 to x equals 3. Those are the bounds on this x function. So when I evaluate it along these bounds, I have to plug in 3 for x, and I end up with 3 times 1/2 times 3 squared, which is going to be 27 halves, times y. That's evaluating it when x equals 3. And then I'm going to subtract out, evaluating it when x equals 0. In this case, when x equals 0, this whole term just becomes 0. So I evaluate the inner integral with respect to x, treating y as a constant. So the 3 and the y just go along as constants. And when I integrate with respect to x, I'm using the polynomial rule to say that I'm raising x to a higher power and then dividing by the reciprocal of that power. Then I evaluate it at the bounds. The bounds are going from x equals 0 to x equals 3. and that's what I get for these two bounds. So we aren't quite done. I'll rewrite this up here. What did we get? We've gotten rid of our x variable, notice. So now we're just looking at an integral from where y equals 0 to 2 of this new function, 27 halves y dy. So now I'm going to do this integration, and really, this is integration that we've seen before, because I just have one variable in here. So when I integrate with respect to y, it's also a polynomial rule. I'm going to raise the y to the next highest power, which is 2, and then divide by the multiply by the reciprocal of this 2, meaning that my constant 27 halves comes along for the ride, and I multiply that by 1/2 times y squared, and then evaluate this from y equals 0 to 2. So I can simplify this a little bit. I have 27 fourths. Evaluating when y equals 2, I get 4. 2 squared is 4. And then I have to subtract off the lower bound when y equals 0, which in this case is just 0, which gives me a value of 27. Algebraically, it has strong analogs to what we did with partial differentiation, in that when I integrate with respect to x, I treat my y variable as a constant. When I integrate with respect to y, I treat my x variable as a constant, although in this case there was no x variable because it had already been eliminated.